Welcome to Lab 8. Today we are going to be discussing how to use a shear plate interferometer and the results we can get with it. I'm Evan, this is Caleb, and that's Logan.
We're going to be looking at interferometers with and without wedges.
We're also going to learn how to look at aberrations on these fringe patterns.
Let's do it.
So when you're testing non-wedged and wedged shear plates, the fringes appear in the region where the light is reflected from the front and rear surfaces of the shear plate overlap. When the beam is reasonably close to collimation, the interference pattern on the screen is still a series of equally spaced straight fringes. In such cases, the wavefront radius of curvature r, given by the shear equation r equals SD over lambda times sine of alpha.
So one of the things we want to consider is the difference between non-wedged and wedged shear plates. So in a wedged shear plate, we actually have a little bit of an angular deviation between one surface and the other. And what this means is that the rays no longer come back parallel to each other. Instead, we have an angular deviation of 2n theta, as we see here. Now, what this means is that we're able to measure more of the tilt aberration in the case of the wedged shear plate.
All right, so welcome to the lab. We have our setup right here. This is our Heaney laser passing through the microscope objective and our pinhole to clean up our beam, which then passes through a 200 millimeter plano convex lens. This is our beam expander right here, and we have it flipped around to minimize aberration so that the curved side is on the right side right here. It is then redirected through this mirror to our shear plate interferometer, where we are rotating about the x-axis perpendicular to the table. And so now we can see the fringes viewing screen right here. So right now we are at our best focus position, which is why this shape is charismatic of spherical aberration. And now if we defocus it, then we can see that we're too far in from our best focus position, and that's where you're going to see all those fringes. And then if we move through the focus positions, we get those two central lobes right there. And so we want to find the balance in between those to balance out defocus, and those residual fringes that we see here are just from our spherical aberration in our system.
So before, we measured the aberrations of on-axis, but now we want to see the interferogram of off-axis. So what we did is we moved our second lens in our beam expander, and we added some decenter. Then we're able to see our off-axis aberrations visualized right here. And here you can see that we see some form of coma. And this is the general shape that we see. It changed from a double teardrop shape that we saw in on-axis to this more elliptical shape that we see for coma.
So what we've done is we've flipped our collimation lens around, and now we're going to observe the difference in the fringes. So here we are at best focus, and you can see a very high difference in the fringes because there's a lot more contrast. You'll see a lot more spherical aberration. And now that we've moved our collimation lens off axis, so we've decentered and also defocused, you can see the ellipticity of this fringe is much higher than it was when it was the proper orientation.
So now we have our second setup, and here we're currently using a 400 millimeter lens and a 200 millimeter mirror, but originally we had a 75 millimeter lens. But the problem was that our range of usable defocus was too small. So we added in our 400 millimeter lens, and now we have a significantly larger range, and so we can actually visualize the fringes on our interferogram. Currently, we have our focal point on the mirror, but in the next experiment, we will actually move our lens back to F, and this will allow us to have an intermediate focal plane right here.
With this setup, we are seeing some spherical aberration, and this makes sense because our source is on axis still, and then we're going to have a lot of spherical aberration coming from our normal collimation lens, but we're seeing a very minimal spherical aberration coming from this lens over here, our test lens. So now we're going to add some tilt to our mirror. So right now Evan is tilting about the x-axis, and you can see the fringes are changing pretty drastically. We're getting much changes in our intensity of our fringes, but if you were to tilt about for the y-axis now, so using the top actuator, you can see we don't actually see any changes in our fringe pattern. It's just translating up and down on our note card.
So as Evan is rotating the mirror, the whole element, you can see as this translates across the screen, there's some clipping on this left-hand side. And the clipping is just because our system isn't aligned as well as it should be. So to avoid clipping in your system, you're going to want to ensure the best alignment possible.
We have moved to a wedge shear plate interferometer with the lens orientation to maximize aberration. As we defocus the lens, the orientation of the fringes will change, and we know that the light is collimated when the fringes are in line with the viewing screen reference line. When you decenter the lens with the wedge shear plate, the orientation of the fringes don't change, but the entire spot just moves up and down on the viewing screen.
Now that the lens has been flipperooed to minimize aberrations, we can see that there's a lot less curvature of the fringes. So right here we are collimated because they are parallel to the line drawn on the viewing screen, and it's going to behave the same way as when we were maximizing aberrations, such as when we decenter the lens, the spot just moves up and down. There's just less aberration in this orientation. We then used MATLAB to measure the fringe positions, and then in this graph on the left you can see we have our data points from those measurements and a polynomial fit, which is very similar to the calculated wavefront shown on the right. And here are our results for tilt, defocus, coma, and spherical aberrations.